What if I told you that even black holes, the most powerful objects in the universe, are slowly dying? It sounds impossible. These cosmic titans, with gravity so immense that not even light can escape, are the universe's ultimate symbols of permanence. But in the strange world of theoretical physics, even the eternal has an end. To understand this cosmic paradox, we first need to grasp what a black hole truly is. They are born from the death of colossal stars. When a star at least 20 times more massive than our sun exhausts its nuclear fuel, it collapses under its own immense gravity. This cataclysmic implosion crushes its core into an infinitely dense point called a singularity, creating a region of space-time where gravity is so strong that nothing can escape. This boundary is the event horizon, the point of no return. For a long time, we believed anything crossing it was lost forever, making black holes seem like eternal cosmic prisons. But in 1974, the legendary physicist Stephen Hawking changed everything. By merging Einstein's theory of gravity with the bizarre rules of quantum mechanics, he made a startling discovery. Black holes are not completely black. They must emit a faint thermal glow, now known as Hawking radiation. The secret lies in the quantum vacuum of empty space, which isn't empty at all. It's a fizzing soup of virtual particle pairs that pop into existence and annihilate each other almost instantly. Hawking theorized that if a pair forms right at the event horizon, one particle can fall in while its partner escapes. To an outside observer, it appears as if the black hole itself has just radiated a particle away. Empty space isn't truly empty. It's a seething foam of virtual particles that constantly pop into existence as particle-antiparticle pairs before annihilating each other. But at a black hole's event horizon, if a pair appears, one can fall in while the other escapes. The infalling particle has negative energy, subtracting from the black hole's mass. The escaping particle becomes real, carrying away energy as radiation. This is Hawking radiation, a process ensuring every black hole will eventually evaporate completely. The rate of this evaporation depends on size. A smaller, stellar mass black hole is hotter and radiates away its mass much faster than a colossal supermassive one. A solar mass black hole would take 10 to the 67th power years to disappear. Supermassive black holes, however, will last for an almost eternal 10 to the 100th power years, outliving everything else. This leads to the distant black hole era. After the last stars fade, the universe will be a dark, cold cosmos, populated only by these slowly dying giants, silently radiating their mass into the void. As a black hole shrinks, its evaporation accelerates, culminating in a final brilliant flash of gamma rays. It erases itself from existence, leaving behind an almost empty universe filled with a faint whisper of radiation. Black holes may be the kings of the cosmos today, but even kings don't rule forever. Through the slow process of Hawking radiation, they will eventually evaporate over unimaginable timescales. Their story is a profound reminder of cosmic evolution. If you're fascinated by these mysteries, subscribe and join our journey. Explore more mind-bending topics with us right here.